Hello class, this is my mini lecture on Chapter 2 out of the Miller textbook. Chapter 2 is Science, Matter, Energy, and Systems, and let me cover just a few highlights of what I think is most important in the chapter. Now it starts out with what scientists do and a description of the scientific method. Now this is one thing that sets science apart from other areas of inquiry. The idea that you observe something in nature, you question it, you form a question, you then come up with a hypothesis as to why what you see is, why is that happening. You test the hypothesis with an experiment as best you can. Sometimes that's not always possible in the real world, dealing with people and ecosystems. It's easier, obviously, in a laboratory. Then you get a result. So what happens? Either that result supports your hypothesis, and you can consider that then to be true, or you come up with a new hypothesis to try to explain how the experiment came out. Then you experiment again, and then you get another result, and then maybe at some point, hopefully, you come to a conclusion. So this scientific method has worked very well for us in dealing with many problems. It's obviously been very successful in terms of developing new technologies and the space program and medicine, and is useful not only in the natural sciences but in the social sciences as well, and sociology and psychology, political science, economics. And it's very important for you to know this, because it's a good way for you to use it to make judgments and study the world around you. And so anyway, you want to take a good look at that. It's why scientists are, look at the world a little bit different than other folks do. Then we're going to study basically matter and energy. So this is a chapter that has a little bit of chemistry and physics in it, and you need a little bit to then go on to the next chapter and understand ecosystems, and then go further on to talk about pollution and so forth. The main thing I want you to learn about matter, much of this you may have learned in your basic high school or basic, if you had other science classes at the college level, is the law of conservation of matter. And basically everybody sort of heard a version of this, that matter can't be created or destroyed. And that we can't create new matter and we can't destroy old matter, because it just changes into something else. We can take a piece of wood and burn it, but it doesn't disappear, those atoms. They turn into ash and into various forms of pollution and smoke that go off into the air. And if you could gather all of that up together and put it together, it would be equivalent to the piece of wood that you originally burned. It's not the same, but you haven't created any new matter and you haven't destroyed any matter. You've changed its form. So the conservation of matter. And this is important for when, for instance, when we come to deal with solid waste. When you throw your garbage out, we used to say there is no such place as a way. Where is a way? You get it out of your house, maybe you even get it out of your town, but it goes somewhere. It gets burned at a plant, maybe. It gets buried in a landfill, which is what happens to most of the garbage and trash in the United States. Something's going to happen to it. There is no away. Your away is somebody else's backyard. And that's a very important concept in ecology and in environmental studies. So the conservation of matter law really does pertain to us, in that you can change the form of something, but you still have to deal with it. Okay, now, then it goes on to energy. And the main thing I want you to know about energy, there's a little bit of physics there about the spectrum and things like that. But basically, there are the two laws of thermodynamics. And the first law of thermodynamics is basically when you convert energy from one form to another, no energy is created or destroyed. So very much like the conservation of matter law. When you convert energy from one form to another, you're not destroying any energy. So when you take the chemical energy in a gallon of gasoline and you burn it in your car, you're converting that to other forms of energy. You're converting part of it to mechanical energy because the pistons turn and go up and down, and then you're able to drive, and so you have mechanical energy coming out of that chemical energy. But a lot of that energy, practically most of it, goes up as heat energy. That's why your car gets so hot. You can burn yourself on the engine. Think of a light bulb, the old incandescent light bulbs that we're trying to do away with. You have a certain form of electricity that goes in, and you get light, but only about somewhere between maybe 10-15%, maybe a little bit more of that light, that energy you put in electricity turns into light. The rest comes off as heat. Again, another reason you can burn yourself on these old bulbs. They get so hot because most of that energy is put off as heat. So you're not creating or destroying any energy. You have the same amount at the end as you started with. It's just that you've changed its form from one form to another, from a liquid gasoline to heat energy or to mechanical energy, from electrical energy to light energy and to heat energy. And then what's probably the most important law for us is the second law of thermodynamics. It basically says when you convert energy from one form to another, you downgrade its quality. And by quality, we basically mean it's a lower form of energy. So for instance, that gallon of gasoline, a high form of energy, lots of energy in a gallon of gasoline. You put it in your car, you drive, you transform it into mechanical energy, and then into heat energy. Well, the heat energy dissipates and goes into the atmosphere. So it's still there, but you can't use it anymore. So it's considered lower quality. It's not a useful form of energy. The useful form was back when it was a gallon of gasoline. And then you've changed it into two other forms of energy, at least through mechanical and heat energy when you drive the car. And so these are considered lower forms of energy because it's harder to collect that heat, let's say. I mean, the mechanical energy you get some use out of because you actually move and you drive. And the heat energy just goes into the atmosphere. So whenever we change energy from one form to another, we come out at what you could consider a qualitative loss. We have energy that is less usable after we convert it for the most part. So again, we take high energy uranium, we put it into a nuclear power plant, we control the fission there, hopefully, and it heats up water that surrounds it and boils water, which turns to steam, turns a turbine and a generator, and we produce electricity. That concentrated form of uranium was a very high quality concentrated form that, as you know, could in other forms can build atomic bombs. Not that nuclear plants cannot blow up in that sense from a nuclear explosion. So it's not that word, but you see how much energy is in that, according to Einstein's, of course, famous equation, which was what? Okay, you got it. E equals mc squared. Energy equals matter times the speed of light squared. Well, the speed of light, is very fast. It's an enormous number. You square that, you get a really enormous number. So energy, let's say the energy you get out of a piece of uranium is equal to its matter, maybe about 2.2 pounds, or a few pounds you need to make an atomic weapon, times the speed of light squared. A huge number. So this is what's important about the second law of thermodynamics, because it has to do with efficiency and how efficient are the processes we use. So, for example, you put that light bulb in, it's only about 10 or 15% efficient, because that's how much light you're getting out. The rest comes out as waste heat. When you use the newer bulbs that we have, the fluorescent bulbs and so forth, and hopefully soon transforming that even to better form, which would be an LED bulbs, which are out now, but they're still very expensive. And there you're converting a much higher percentage, not 100%, but as you know, those bulbs don't really get very hot. You can touch them because they're turning most of the energy into light energy. So they are more efficient, and so you have lower quality energy, let's say, at the end coming off of heat, which is not why you for the most part, use a bulb, except in a little toy oven. Well, what do they used to be called, those toys? Anyway, you bake in the little oven. So using a light bulb. And this is an important concept for all environmental areas, because that whole concept of efficiency, if we can be more efficient, it means we're using resources more effectively and more wisely. And so this is a very important law, probably the most important aspect of physics, really, that comes into play when we study about the environment. Okay, then the chapter goes into the concept of systems. Of course, this is because we're going to study ecosystems. And so a system is operating, there are interrelations between different parts of a system. Something comes in and it affects the system. You know there's going to be a reaction, what's going to happen. So we have an ecosystem by your house. Let's say it's a lake and a field around it, or a forest. A developer comes in and fills in the lake or chops down the trees, and we put in houses or buildings. Something's going to, obviously, something really changed in that system, and there's going to be a reaction to that. And, probably a fairly negative reaction as far as ecology is concerned, because we're going from maybe a diverse ecosystem to one that's not very diverse at all, in terms of maybe having a few houses and plants that weren't even native to the area being planted there, and so on and so forth. So this idea of studying systems analysis, systems thinking, is something which really is an aid to looking at environmental issues and problems. Okay. Let's see, what else do I want to mention? Yeah, there's a little bit more on systems, and I think that's pretty much it for that chapter. Those concepts, the scientific method, the laws of matter and the two laws of thermodynamics of energy, and the idea of systems and so forth. These are important concepts, based in chemistry and physics, that are really important for the study of environmental issues. So take a good look at those, get a good basic understanding of those, and you should be able to apply those to much of what we study later on. So that's it for Chapter 2, and I will see you next time on Chapter 3 of the book. Bye.